duality. So this is the reason why, if you took Math 221 with me, this is the reason why I insisted on using rows and columns instead of making everything a column vector, is duality. We're going to go over this today. So let's fix a vector space V over our field F. The dual of V is, okay, there's a mistake in the notes. That should say V prime and not just V. No. V prime is homomorphisms from V to F. Now F is a vector space over itself, right? F is really F to the 1. It's the vector space of dimension 1 with basis just the element 1 in the field. And that's Hom. People will write this way, Hom from V into F. Okay, that's just notation.
Professor Miller?
Yes.
The notation V over F, is that distinct from V mod F, or are they the same concept?
Oh, no, it's definitely, this is just a, no, it's definitely different.
Okay.
It's the vector space V over F. It's just the slash is just used for as a shorthand for over in that case. So I guess you have to take that for context. Yeah, V modulo F doesn't make any sense because F, well, it could make sense, but there's no canonical way to view F as a subspace of V. So let's just leave it that way for the moment, like this. Okay, so lemma. So the elements of V prime are just homomorphisms from V into F. So the lemma is that V prime is a vector space over F. That can't be confused. So proof, this is just a check. So it's something you have to check. So if you have L, that's going to be, L stands for here linear function. You should view this as linear functions from V into F. So I'll use L for a generic element in there. And alpha is in F. So that's a scalar. This says if you have a vector, so this is a dual vector, if you like, and a scalar, then what happens? You get alpha L, right? We have to know that there's the action of F on the vector space V. We have to know what scalar multiplication does. What does it do? Alpha L adds V to alpha L of V. So it really just scales things. What is alpha L of V? See, L is linear. So this is L of alpha V, right? And the point is that I have to tell you which linear function this is. This is the linear function that does L, and then it multiplies by alpha, which is the same thing as multiplying by alpha and then doing L. That is an element of, so this is in V prime. That's in V prime, so check. That's good, right? And now I need to know that if you give me two linear functions, L1 and L2, if those are both linear functions on V, then L1 plus L2 from V, that takes V2, and you can guess what you're going to define it to be. It's just going to be L1 of V plus L2 of V. So that's in V prime. And there we go. You have to check the axioms for sort of associativity and these sorts of things, right? But that's something that I'll leave to you. The point is that V prime is You know what the structures are. You know what multiplication by alpha does, and you know what summation does. And now you just have to check that this makes V prime into a vector space. But we actually know that it does, right? Because we actually showed that last time. We said that if we have functions, so if we have any functions from V into anything, then that's going to give us a vector space. We showed that at actually we showed that in 221. So functions from anything to, as long as you're taking your functions from something into a set F, which you can add and multiply by scalars, that makes the functions into a set. You just have to check that that set now is, you have to check that the linear ones are closed under addition and scalar multiplication, which is there. Right, so really what we're doing is we're checking that this V prime is a subspace. So this is the size of functions from V into F is a subspace. And that's what we need. Right, if we take all functions from V into F, that's a vector space that we actually checked in Map 221. And then inside of that, to check it's a subspace, you just check that it's closed under addition and scalar multiplication, and you're done. Questions about that?
So again, what have we proved in 221 for the set of functions from V to F?
We proved that the functions from any set into the ground field is a vector space.
Okay.
The set of all functions. And then what we did was we said, okay, well, what if you're looking at functions into R? What if we had functions from R to R? What if we look at continuous functions from R to R? What if we look at differentiable functions from R to R? And the point is that to check that those things are vector spaces, you only have to check that the sum of continuous functions is continuous and a scalar multiple of continuous functions is continuous. You don't have to check all the axioms because you know that all functions from a set into R, that's a vector space. All you have to check is that when you have some extra condition that it gives you a subspace. It's much easier to check that something is a subspace than to check that's a vector space to begin with.
Professor, just a quick thing here. So V prime is the set of homomorphisms. And so
Yes.
a set of homomorphisms is a stronger statement than the set of all functions. And so that's what you're saying there.
Yes, that's the point. So you just check that, that's exactly what I just said. So V prime is a set of functions. But it's just like if you look from functions from R to R, so the set of all functions from R to R you verify as a vector space because functions from any set into R is a vector space over R. And then what you say is if you want functions with a certain extra condition, you check that that's a subspace. So this is the subset of all functions. It's the subset of linear functions. And the point is that linear functions are closed under scalar multiplication and addition. The sum of two linear functions is linear. The sum of the scalar multiple of a linear function is also linear. Yeah? Okay. So for example, one. So let's take V to be F n column. So we're taking column vectors of size n. Then what is V prime? I'm going to write equals, even though what I really mean is canonically isomorphic. It's F n row. Now, it isn't actually equal to the row vectors. There is a canonical isomorphism from the row vectors to the dual vector space. So it's really, I should write isomorphism, but it's a unique isomorphism, and I haven't made any choices. There's no choice of basis that has to happen. There is actually already a choice of basis that has happened, but let's not worry about that for the moment. So what's the idea here? The idea is that if I take y1 up through yn and multiply it by x1 down through xn, that gives me y1 x1 plus yn xn, and that's an element of the ground field F. So the point is that every row vector acts as the linear function that takes x1 through xn to this linear combination of x1 through xn here. This is a scalar, right? This thing is a scalar. Yeah, so every row vector gives you a linear function on column vectors. And I claim that every linear function on column vectors is given by some row vector.
Excuse me, can you explain the notation of how you wrote that?
Oh.
Like the Fn call Fn row.
Oh, these are just column vectors of size n, and these are row vectors of size n.
Okay.
I'm just saying that every row, that's saying that row vectors are the same thing as functions from column vectors into the field. And here's how you do it. This row vector gives you the, if you like, I can write it this way. Let's have a little bit of fun. It takes, yeah, that's how I'm going to do it. It takes this thing to that thing. Yeah, okay. This will get deeper as this particular lecture goes on. We'll do more stuff with this example. So let's take V to be the continuous functions on the closed interval from 0 to 1. Then there is a linear function which is integral from 0 to 1 of your thing, whatever it is, dt. That is an element of V prime. Right? So the operation that takes a continuous function and gives you the integral from 0 to 1 of that function. That is a linear function on the vector space of continuous functions on the interval, closed interval 0, 1. So what does that do? It takes, let's say, this thing takes, so integral from 0 to 1 dt, it takes f to the integral from 0 to 1 of f of t dt. And the point is that that's linear. Yeah, integration is linear. This is something we also covered in 221. Actually, it's something that you covered in calculus, and then we mentioned again in 221 as a statement about vector spaces. 3, let's take V to be the one-time differentiable functions. You know what, let's do another example inside of 2. Sorry, there's one more I wanted to do over here. And that would be, let's take evaluation. Evaluation at the point 1/2. That's also in V prime. So ev 1/2, it takes every function f and it takes it to f of 1/2. That's also linear, right? Because if you take, just by definition actually, because if you take f plus g, then f 1/2 of f plus g is by definition f of 1/2 plus g of 1/2. And if you multiply it by 3, then you get 3 times f of 1/2. So it's actually this.
What's this ev?
It's evaluation. Here it is. I've just defined it.
Oh, okay, okay.
It stands for evaluation, but it takes every function to the evaluation of that function at 1/2. I had to choose something in the interval 0 to 1. That's all.
Would each of these examples be under different fields, or are these all in V dual over a certain field?
This is over an arbitrary field. This has to be over R because it's integration. This one will work over any F, except for the fact that it's defined, the vector space is over evaluation at any field element. If you're taking functions from, okay. The way I've written this example is all over R, but if you had functions from something to your ground field, then evaluation at any something will still be linear. Ben, did you have a question?
Yeah, in the first example, did you say that V dual is uniquely isomorphic to Fn row?
What I would say is that in this example over here, what I would really say is that there is a natural, or if you like, canonical isomorphism V dual to R, sorry, to F and row.
Because those row vectors, the way that you're acting is through matrix multiplication, right?
Yes.
So could you also say it's isomorphic to Fn column, and then they're just acting through like the dot product, what you can define?
So the dot product is a choice. It's a choice of inner product. And actually, it's a choice of, it's not really an inner product, it's only inner product if it's over R or C. We'll get to that shortly. That's going to be a choice of how to make a vector in V, how to make a vector in a vector space behave like a linear function. How do you make a vector in a vector space into a linear function? You have to choose an isomorphism of V with V dual. Whereas this one, there is already there is a canonical choice of how row vectors are dual to column vectors. In essence, it's because this thing comes with a basis, and so it has a dual basis. So it's sort of, when I say it's natural given the choices I've already made. And what I've already made for the Fn call is a choice of basis. Otherwise, it would just be abstracting a vector space of dimension n, and then there would be no way to write what a row vector versus a column vector is. The fact that they are columns means that there is a given basis. Yeah, it's a good question.
Professor Miller.
Yeah.
So for in the second two examples with the integral and the evaluation, is this saying that for each like homomorphism from V to F, like it corresponds to exactly one, like for instance, integral from 0 to 1?
No, I'm saying that the integral from 0 to 1 is a homomorphism from V to R.
Can all homomorphisms be represented as those integrals?
No, here's one.
Oh, right, yeah.
On the other hand, people like to view this one as an integral. What they'll do is they define the Dirac delta function. And they you view that as the function that looks like this. So if you're integrating the function on 0, 1, so here's 0, here's 1, right? And what you're going to look at is a function that's 0 everywhere except it's sort of infinite here, and you want the area to be 1. And you view this as a delta function. Then the integral of this function versus f would actually be the evaluation at 1/2. Right, so you sort of put all the mass of this function at the point 1/2, and then when you integrate this against f, what you get is f of 1/2. And you can view that as a limit, right? It's if you take functions that look sort of similar to this but aren't quite there. So if you take a function that looks like, this, and you take a sequence of these guys and you let them approach this thing, then you'll find that this thing is a limit of actual integrals, but it's not an integral of an actual function. Nonetheless, you can think of this being as an integral of an actual function if you think of this delta function as being a function, which it's not, because the height here would have to be infinite in some sense.
I was wondering because I was trying to think of like, I guess isomorphisms between, like an isomorphism between like V and V prime, but like, and like the set of those integrals being isomorphic to the continuous functions in some sense, but.
You win the prize for the day. So that is the next line in my notes after we finish the example, is how to do an isomorphism from V to V star.
Oh, okay, great.
Yeah, so, and it's not going to work here because this is an infinite dimensional space. So when you have an infinite dimensional space, then you can do you can try to approximate things with finite dimensional spaces, but what you find is that you need to take completions. That's why it's important that this thing is a limit of these dual vectors that are integrations, but it's not actually an integration itself. Yeah, good. So just for one more example, let's just take V to be C1 of the whole real, so that's the one-time continuously differentiable functions. Then I claim that evaluation at 1/2 composed with the derivative, I claim that's in V prime. And what it does is it takes f to, what does it do? What happens when you compose evaluation at 1/2 with differentiation? What should I put here? Where does it take f? F prime of 1. Good. And that's linear. Why is it linear? It's linear because differentiation is linear and evaluation is linear, so you can compose them. Have fun, by the way, expressing this differentiation in terms of integration. No. Yeah, but, so as a matter of notation, we'll often write, instead of L of V, we'll write it as a bracket L comma V. Can you all see this part of the board? Online? Good, it's still there. Okay, so you've seen this notation before. Where have you seen this notation before? Particularly this is for Ben now.
Inner products.
Yeah, this is for inner products. Why is this for you? Because it's relevant to this question over here. So the choice of a basis is going to give us an inner product, which is why Fn rho, anyway, which is why we get that isomorphism, because we've already chosen the basis. So why do we want to use the same notation for inner product? Remember, inner product is you take two elements of the same vector space, and then you kind of, you do something with them. It's a rule for taking two elements of the same vector space and getting a scalar. And so I want to say why these notations are the same, why they use the same symbols for that. So, I mean, for one thing, from Noah's question, you should be viewing V and V prime sort of on equal footing, because V gives you a linear function. So V prime gives you linear functions from V into F. By the same token, V gives you linear functions from V prime into F. So they are dual to one another. So let's just see what happens in our sort of situation from before. Suppose that you have a linear map from V to W. When I write this, you should think that V is a vector space, W is a vector space, and phi is a linear map between them. So it's a homomorphism. Then, if you give me L in W, right? So you have a linear function on W, right? So this is L in W. Then I claim that this implies that if I take L and compose it with phi, that is going to be inside of V prime. So that's L in W prime. This should say W prime. Right. So what I want to do is this. L. Right, so if you have a linear map from W into F, you have a linear map from V into W, when you compose that, you get a linear map from V into F. Yes, Ben?
Do you need to write L composed of P as in V prime? Or
V prime. I meant V prime. I don't know what's written here, but yeah, what's written here is also right. It's correct. Yeah. So it says that if you have a homomorphism from V into W, then you can take linear functions on W, they automatically get sent to linear functions on V. Now that sounds kind of backwards. So let's just write some of this stuff down and see what we get. So there's going to be some, so phi prime, so you should think of this as being the dual of phi. Actually, I want you to think of it as being the transpose of phi. If you see, you'll see why shortly. So think of this as being a transpose. Then phi prime, if that takes L to L composed with phi, then this is a map from W prime to V prime. That's the map that we just did over here, right? It's the one that takes the blue things to the red things.
Oh. Just made some noise, my apologies.
Oh, okay. So what does this mean? So now let's look at the notation. So the notation says that if we take phi prime and apply it to L, so what is phi prime applied to L? V prime applied to L is now a linear function on V. Sorry, V, right, yeah, so L is a linear function on W. And now V prime of L is a linear function on V. So I can now apply it to an element of V. Like this. Right, now what is that equal to? By definition, that is L composed with V applied to V, which is now L applied to V of V, by definition. Right? You just have to look back at this diagram the whole time, right? Right, so if I take L of V and I apply it to an element in here, it's the same thing as taking the element in here, taking phi of it, and then applying L. So this is what I want you to see. It's this symmetry here. Right? If you do phi on one side, it's the same thing as doing phi prime on the other side. Now let's think about the example. In example 1, right? So now what we've got is we've got Fn. Where do I want to write this? Fn call to Fm call. So how do you write down a linear map from column vectors of size n to column vectors of size n?
Multiplication by matrix.
Yes, multiplication on which side?
Wait, from n to n.
It's from n to m. So first of all, what's size matrix? And where do I multiply it?
Do an n by n matrix and
Yeah,
column matrix, and you can only left multiply.
left multiply. Good. Okay, that lambda stands for left multiply by. Lambda is the Greek letter L. So this is left multiplication by A. Okay, so what would the dual be? So if I had F m row, right, that's the dual to Fm call. Then I have a map to F. Let me write this somewhere else. Let me write it up here. So we have F m row mapping to F n row. Suppose that this is right multiplication by A. And it's the same matrix. Okay, it's not the transpose matrix, it's the same matrix. So what's the point here? The point is that y, and then left multiplication by A of x, what is that? That's going to be y ax, yeah, just by definition, because left multiplication by A of x is just 8 times x. And that's y ax. Right? So now this is, remember, this is now sort of Fn call, and this is Fn row, which is Fn call prompt. All right, so this is the pairing of linear functions. So this is saying linear functions on a vector space. That's what this is.
I'm having a hard time reading those Fs that you just wrote. Can you say them aloud or?
These little things I just wrote?
Yeah, I can't read them.
Let me write them bigger.
Thanks.
That's why I raised them right bigger. So this is in Fn, this is in Fn call, and this is Fn row, which is Fn call prime. Is that better?
Yes.
Okay, so that's YAX. And then YAX is also YA paired with X, which is row A of Y paired with X. So what we get is this thing. So this means that right multiplication by Y, this says that right multiplication by A, I'm sorry, is left multiplication by A dual. Remember I told you should think of this as being transpose? You should think of this as being the transpose to left multiplication by A. How would the book last semester, when you took 221, I know it wasn't last semester for a lot of you, but when you took 221, the textbook, if you took 221 here, the textbook always treated everything as column vectors. So this is the right way to view this thing. There is also a wrong way to view this thing, which is that the dual to this picture is the picture where you have Fm row, and now let's see, this is going to be Fn row, sorry, not row, these should be call, this way, and this is going to be now left multiplication by A transpose. Right, so this picture is literally the transpose of this picture. This picture I find confusing. This picture is correct. Yeah.
When you label the F, call, N, which one is it?
Where are we looking here?
Um,
Oh, that's this.
It's the whole thing.
No, it's that. And this one is this.
But if you have lambda A applied to X, shouldn't it be F, call, M?
Oh, yes. Yes, you're correct. Just a second, let me think for a second. B prime L. Yes, okay. So let's be a little bit clearer here. This one, this is in Fn call. These are Fn call. How do I say this? Fn call and Fn call. And this one, you're correct, is Fm. So this one is for Fn, and this one is for Fm. Yeah, so this side is the Fm side, and this is the Fn side. So this is the Fn side, and this is the Fm side. Yes, I'm sorry, I wrote the wrong thing. This should be Fm. Yeah, so keep in mind, again, composing with phi takes you from a linear function on Fn to a linear function on Fm. So when you're pairing linear functions, you don't have to be careful. That's the whole point, is you don't have to be careful, actually. What goes on the left-hand side is something that can be paired with something that's on the right-hand side. This is the main thing I want you to take away from it. Is that the transpose, the dual of left multiplication by A is right multiplication by A. And it's the same matrix, right? The same matrix takes column vectors of size n to column vectors of size m. right? So if these are column vectors of size n, these are column vectors of size m, and multiplication by A takes column vectors of size n to column vectors of size m. On the other hand, it also takes row vectors of size m to row vectors of size n. Yeah, so this map over here is the ordinary one you get from linear algebra. We have a vector space with a basis, and then you write down a matrix for that vector. You write down a matrix for the linear map that goes from this vector space with basis to that vector space with basis. The dual of that is a homomorphism between the dual spaces. Here they are. Here's the dual space to this one. It's row vectors. Here's the dual space to this one. It's row vectors. And the induced linear map from the dual space here to the dual space here is given by right multiplication by the same matrix. If you were to now view elements in this dual space as being elements in the original space, Ben, this is what your question was about. If somehow you were to identify column vectors with row vectors, then what you say is that the dual to multiplication by A is multiplication by the transpose of A. So transpose has this meaning of it's the dual given the inner product on this vector space, which identifies column vectors with row vectors. The dual to multiplication by A is multiplication by A transpose. Yeah.
Okay, so A and A transpose, if the multiplication and different are like the dual vector spaces, then how can you have a matrix's inverse, like you do with orthogonal matrices, to be some transpose?
So you just said the word orthogonal. What does orthogonal mean?
Orthogonal means that, well, when you take the inner product or I guess multiply.
You said inner product. So you've chosen an inner product. So in order to be orthogonal, you have to have chosen an inner product. Once you've chosen an inner product, so we're going to get to that in just a second, you've chosen an isomorphism from V to V dual. Right. That's exactly the point, yes. So in order to write down what it means to be orthogonal, you have to have chosen enough information to get this isomorphism from V to V dual. That's exactly the point. So when we do, so we're going to do inner products now. We want to make sure that this notation is all compatible with inner products. But when you did this in 221, you did it over the reals. Raise your hand if you've seen inner products over the complex numbers. Okay, just out of curiosity, in what courses did you see them?
Quantum mechanics.
Very good, yes.
Yeah.
Say it again?
Wikipedia.
Wikipedia, yeah, good enough.
Oh, yeah, yeah, just online.
Oh, online, very good, very good. Raise your hand if you have seen the geometry of the complex numbers.
Professor, I just wanted to say we did inner products of complex numbers in 218.
In 218, oh, very good. Who taught that?
Brian Fitzpatrick.
Okay, very good, very good. Okay, raise your hand again if you've seen geometry of complex numbers. So if I say e to the I theta, you know what I'm talking about? Yeah, okay, let's do it again. Let's just do a quick review of geometry of complex numbers. This is going to come up a lot in this course, especially exponential things, so I want to make sure we're all on the same page. And that page is this page right here.
Professor, just before this page, a quick question. So in the matrix example that you gave there, you have the maps to from N to R on the top.
I'm sorry, where are we looking?
Yeah, that's exactly where you are, exactly where you pointed.
It says N to
yeah,
M.
exactly right there.
This is
So that maps to goes from N to M, and then the one on the bottom goes from M dual to N dual.
It's M dual to N dual.
Yes.
Yeah.
All right. Perfect. Thanks.
Yeah. So in general, what you write here, you have V going to W, and then you'd have W prime going to V prime, and this would be phi, and that would be phi prime. So this picture is this picture. These are a specific example. Yeah. Very good. There are no inner products in what I've written down here. Everything that I've written here is pairings of linear functions with elements of the original vector space. I want to be clear about that, right? We haven't actually used inner products yet. We haven't done any inner products. All of these things are, this is Feng's question. This is all occurring in f to the n and f to the n dual. This one is occurring in f to the m and f to the n dual. Right? It's not, we don't have elements of f to the m and f to the n. They're elements, they're either vectors or they're vectors paired with linear functions. The geometry of C. So C is just A plus BI such that A and B are real numbers. I assume that you have seen that. That is a vector space over the reals. And the basis that we've written down here is just 1I, where I is a square root of -1. And one of the interesting things about mathematics is it doesn't matter which square root of -1 you choose. We choose one in order to make multiplication go counterclockwise. Why we do that is probably because the people that were following who did this were right-handed. There's probably no other good explanation for it. Because, see, you draw 1 over here going to the right, because, you know, we write right-handed. We write from left to right. If this notation had been invented by Israelis, then everything would be backwards, because the 1 would be over here, because you write this way. And it's natural, I say natural, although it's not actually natural, but it's natural to put the square root of -1 pointing up. But there's no really good reason for that. We could just as well have put it going down. So if it had been invented by Chinese, it would have been rotated again, because then you write downward. Anyway, in any case, this is going to make our multiplication go this way, as we'll see. So the conjugate of Z, which is A plus BI, the conjugate of A plus BI is Z bar is A minus BI. So Z maps to Z bar, this is conjugation, and this is an automorphism of the complex numbers, by which I mean an isomorphism from C to itself. So it's an isomorphism of fields, and it takes C to itself. It's an R linear automorphism, actually. This is a linear map from C to itself. R linear map. It is not a C linear map. It is an R linear map from C to itself. Okay. How about Z bar? What is Z bar? That's the square of the absolute value of Z, which is A squared plus B squared. Which is also A. By definition, it's A plus BI minus BI because it's Z times Z bar. Okay.
So what's that nomenclature V dot S dot R that you wrote there?
Vector space over R. It's me being lazy. So Z, another way to write a complex number is as R e to the I theta, where R is the absolute value of Z, which is also called the modulus of Z. And theta is called the argument of Z. And the picture is like this. So here we have our Z, there it is, and there's theta, and then this length over here, that's R. Right, so that's the real axis, this is the imaginary axis. Yeah? Okay, so then what is ZZ prime? if I multiply two complex numbers, so if I draw another one, let's say over here. And then I want to multiply these two complex numbers, what is the end result? What does it look like? Those of you who know the answer, wave your hand in a way that indicates you know the answer. No. I was like, show me the answer with your hands. Yeah, it's kind of going to do this. Where should I draw this? I won't draw it in blue. Where should I draw the red line that is the product? Add the two angles. That's what I'm looking for here. So whatever this angle is here, that's going to be theta prime. And then I'm going to add theta prime to here, like this. That's now the angle theta prime. And I'm going to do this. And that's z prime, like this. Yeah? And then it's the product. And you know from the way that I wrote it here, that's going to be r e to the I theta times r prime e to the I theta prime, which is then going to be r prime times e to the I, and then here theta plus theta prime. And that's algebra that can be worked out. It's sort of forced upon you. Here, e to the I theta, what's that? That's, anyone remember what this is?
Cosine theta plus I.
This is cosine theta plus I sine theta. And the question is why? Why is e to the I theta cosine theta plus I sine theta?
You get it from the Taylor expansion of e,
What?
the exponential function.
Excellent. So let's do that first. So there's one reason is the Taylor expansion of the exponential. So let's write down the Taylor expansion of the exponential. So why? There's two reasons. So answer number one is that the Taylor series. What is the Taylor series for e to the IT? What's the Taylor series for e to the x? All of you should know this. Okay, so x is IT.
Squared.
So what's I squared? So it's going to be minus 1 times t squared over 2 factorial. And then we're going to add, now we're going to take I cubed, t cubed over 3 factorial. Right, now I cubed is what? Minus I, right? Then what? It's going to be t to the 4th over 4 factorial. And we're going to get I to the 4th. What's I to the 4th? I to the 4th is 1. And then it's going to be, again, minus, plus I t to the 5th over 5 factorial, dot. I won't even write it. Whether it's a plus or minus. The next one's a minus, but that's, I don't want to write the next symbol. Okay, so now what do? You collect the terms that have i's in them, and you collect the terms that don't have i's in them. And what you note is that the ones with i's, the ones without i's, that's going to be 1, and then minus that, and then plus that, so on and so forth. And so that's cosine of t. And then when you take the ones with i's in them, it's that, and that is plus I sine t. So that is a good reason why cosine, why e to the I theta is cosine theta plus I sine theta. Is there another reason? Good geometric reason? Yeah.
You could think about the unit circle and like the y-axis is sort of like the y's.
Okay, so you think about the unit circle, that's correct. So how do you want me to express the unit circle that makes it clear that this should be, e to the I theta should be cosine theta plus I sine theta?
You have like the I coordinate, it's like I0 or 0 I mean.
Yeah, I mean, I can draw this. When I draw this parameterized curve, it is the unit circle as I move theta. But why should that be? I mean, it is true that when you do it that way, that you get the parameterized circle. When you move theta from 0 to, it being all reals, you sort of go around the circle infinitely many times. But why? So the reason is
What do
that
you mean, why?
why should moving theta along all the reals go along the unit circle in the complex numbers?
This is related, but if you want it to comport with the real, like with how E works in the reals, you want it to be its own derivative. So it should.
You want it to be its own derivative. That's what I wanted to hear. So if you took Math 221 with me, you saw this as the first example of an abstract vector space. We tried to solve the equation f prime equals f. And we found that the answer was the exponential. So the exponential satisfies a differential equation. So the ODE for e to the IT, what does it say? It says that d dt e to the IT is equal to, well, now the rules for differentiation tell you this has to be I times e to the IT. Okay, so now if z, so what we just said, the derivative is multiplication by I. So now we just have to figure out what multiplication by I does. And that we can figure out from the picture we've already done. So if we have z being a plus bi, then what is iz? Iz is going to be negative b plus ia, or from plus ai, right? And now we can draw that picture, and that picture looks like this. So if this is again our z, then what we do is we take a right angle, and this will be iz. So we can easily calculate directly that multiplication by I is rotation counterclockwise, and that's because we choose our 1 and our I in that orientation. It's rotation counterclockwise by pi over 2. Right? So then the question is now, what curve has the property that the tangent vectors are orthogonal to the original vectors on the curve? And now we end up with the answer being it's the circle. Which circle is it, by the way? So it's a circle centered at the origin. Which one? That says circle centered at 0. Which circle centered at 0 is it? How do you know the radius is 1?
Basically because when you plug in t equals 0.
Right, so it's radius 1. So it's the unit circle. Good. So for example, if I took z to be the complex number minus 1, what is the absolute value of z? You didn't have to know it was a complex number for this, right? The absolute value of minus 1 is 1. What is the argument? What is the argument? How far in angle is minus 1 from 1 in the complex plane? That's pi. So what does this formula say now? It says that e to the I pi is equal to minus 1. You guys recognize this one? Has a name? This is Euler's formula. It's great because it has e and I and pi and minus 1 all in the same formula. There's another one, there's another version of this, which actually I think is almost better, which says that e to the I pi plus 1 equals 0. And that has 5 of the fundamental constants in it, and not just 4. It leaves off minus 1. But 0, I think 0 is actually a bigger mathematical advance than minus 1. People knew negative numbers before they knew about 0. Well, that's pretty strange. Okay, so this is a the geometry of complex pairs, we're going to be using that more and more as the course goes on, especially when we do B groups, which for those of you doing quantum mechanics will be really useful.
Professor, just a quick question here. So I know that like one of the the characteristic property, one of the intrinsic properties that defines the exponential function as a whole, it's its own derivative situation there.
Yes.
So, but to affirm what the I does there, we had to like define the complex numbers in a particular way already, so that I times e to the it has the geometric meaning that we wanted to have.
Well, we didn't want it to have a geometric meaning. It just had the geometric meaning already. Like whatever multiplication by I does, it certainly does this.
Yes. Yes.
So maybe you're complaining about me saying that this is a right angle, which is not an unreasonable complaint.
Yeah.
Right? Is that what you want? This being a right angle is the operative point.
Yeah.
Regardless of how we define angle, this is a curve inside of the complex numbers, e to the it, and it has this tangent vector. So regardless of the geometry that I've written down here, the uniqueness of solutions to ODE says that there will be a curve. And I guess you could draw it in a different way. It wouldn't have the kinetic interpretation of a curve in the plane and this being the tangent vector unless you draw this as a right angle.
Okay, that helps though. It helps me understand the association between the geometry and the ideas behind it. Thanks.
Right. Yeah, so your complaint is a really valid one, which says that when I drew the original axes, I drew them as orthogonal to one another, and there's nothing that should make me do that. But this should make me want to do that. Yeah. Okay. So, and here's now. So now we're going to do inner products, but over possibly complex spaces. A Hermitian inner product on a vector space V over R or C. And when I mean R or C, I'll write it as a boldface F, because I don't want to have to specify every time. And that's going to be a function. And the function is going to be V cross V to F. And it's going to take pairs V, W, and it's going to take them to something that I'm going to write as bracket V comma W using the same notation that I used before. But this time, both sides are in V, as opposed to one of them being in V and one of them being in V prime. And we're going to see why that notation actually isn't confusing. It's because when we wrote down the notation before, there was always a choice of an isomorphism between V and V prime. That would, when you have an inner product, it's giving you a choice of an isomorphism from V with V prime. And we'll get to that shortly. And it's going to be, and it has four properties. One, it's linear. So if I take alpha x plus beta y and pair it with a vector z, then I get alpha x paired with z plus beta y paired with z. So it's linear in the first coordinate. So we'll see that this is going to be sesquilinear. So linear in first coordinate, or in the first entry, that says in first entry. 2, I want it to be conjugate symmetric. So what that means is if I take x and y, and if I switch them, y, x, then I have to take the complex conjugate. And you'll see what that means shortly in the sort of principal example. I want it to be non-negative in the sense that if I take x and pair it with x, remember these are vectors in a complex vector space, right? But I'm going to want this to be a real number that's at least 0. And that's for all x in V. And actually, I want it to be non-degenerate. And that would mean that x only gives you 0 when x is 0. The other direction of this if and only if is definitely true. So let's just do that. 0 paired with 0 is 0, and I want that to be the only thing. So the example you should keep in mind is that when V is c to the n, that Z paired with W is supposed to be V1 W1 bar plus dot 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 plus Zn Wn bar, like this. And what is that? That's going to be W bar transpose times Z. And this is the thing that we're going to view this W bar transpose as going as a linear function on these things. So here's the definition for a matrix that's n by n with entries in this real or complex numbers. Its adjoint is A star, which is A bar transpose. So you take the complex conjugate and you take the transpose. Is this still on the board for all of you online? Yeah, good. Let me go back to this linear bit here. Actually, this linear bit over here, what I really want to write here is sesquilinear. Why is that? What would happen if I took the linear combination on the right-hand side instead of the left-hand side?
The scalars are complex conjugate.
The scalars would be complex conjugate. Why? How do you use the axioms to prove that?
By axiom 2.
Say it again?
By the second one.
By the second one, that's right. So if I take x and then z, alpha z plus beta w, then that's going to be alpha bar x z plus beta bar x w. And that's because when I switch them, I can switch the two, then pull the alpha and the beta out, and there'll be bars at that point, and then put them back. So sesqui means 1.5. Here's a note. That when F is just the reals, then A star is just A transpose. This is what you're used to seeing. And now let's do a check. And the check is that if I have V mapping on a matrix A to W, then what I get is the pairing of W with AV. And now we're looking at, now we actually have our, this is now an inner product on W. So that's the inner product on W. That's going to be what? That's going to be AV star times W, which is V star, A star, W, right? Which is that. I can put parentheses around that if I want, and that's just going to be now A star, W, V, which is what we wanted. So then this finally is the answer to the question that you were asking. These two notations really do agree, but they agree because we've chosen an inner product on W. There is a notion of inner product. So if there is a notion of inner product, then the adjoint works the same way that the dual does. So the point is the adjoint is a dual. It's a duality. And now to answer Noah's question next, I'll say out loud the next list. So everything that you saw in 221 still works here, and we will do some of it actually over again. But the triangle inequality still works, the Cauchy-Schwarz inequality still works, Graham-Schmidt orthogonalization still works. It's the same algorithm actually, it's just that you allow the input to be complex, but the algorithm is exactly the same. Least squares still works, the spectral theorem still works. The spectral theorem is something that we will do more about later in the semester. Talking about real eigenvalues and stuff, because that's actually interesting, you have complex matrices. And relations among the fundamental subspaces, so the kernel of A is equal to the image of A star perp. You should check that, it's one of those things. Understanding that is kind of valuable. So I want to answer Noah's question here. And that is that if you fix V with an inner product, jump is too short. If the dimension of V is finite, then the map that takes a vector V to the inner product of V with stuff. So what this does is it takes an element of the original vector space V and it makes it into a linear function. Right? So if you view little v as being fixed, but the right-hand entry is varying, then as a function of the right-hand entry, this thing is linear. It's actually complex linear. It's actually sort of conjugate linear. But this induces an isomorphism. From V to V prime.
This reminds me of the isomorphism between like V and V's quotient with its kernel, or the kernel of the map between the two.
You mean the isomorphism between V modulo the kernel and the image?
Yeah.
First isomorphism theorem, which isomorphism does it remind you of?
I might be getting things mixed up. Forget I said that. I'll think about it more. Sorry.
I will forget you said that at the moment. You can come back if you figure it out. So any orthonormal basis E1 up through En maps to, so that's with V, it maps to the dual basis. The dual basis is going to be E1 prime up through En prime of V prime, such that the point being that Ej prime of Ei is 1 if I equals J, 0 if I does not equal J, and that's what we often call the Kronecker delta function, delta Ij. So I'm leaving out details such as this is a homomorphism from V to V prime. That's very easy to check, and just because of the fact that it's linear on the first variable, right? And then all you have to check is that it's injective and surjective. Well, if it takes a basis to a basis, then you're done. And so now you just check that when I stick a basis vector in here, if I take E1 and pair it with E1, I get 1. And if I take E1 and pair it with E2, I get 0. It's because it's an orthonormal basis, right? The orthonormality of the basis says exactly this, that this has a dual basis like this. And this basis is defined by the pairing. Right? An orthonormal basis is exactly one such that EI paired with EI is 1, but EI paired with EJ is 0 if J is not on. Yeah.
If you don't fix the end product, is it still isomorphic?
So it's abstract, but well, okay. So so you win the second prize, which is I don't mean that I don't mean it's subservient to the first in some way. It's the second first prize. So that's the next line in my notes, which is more generally, a non-degenerate bilinear form gives you an isomorphism from V to V prime. So you don't need an inner product, but a choice of an isomorphism of V with V prime is the same thing as giving a non-degenerate bilinear form. Because so I haven't defined non-degenerate bilinear form, but it's more or less inner product without the positivity stuff. So you don't require things to be positive, but you do require there to be a pairing between vectors, and you require that it be non-degenerate in the sense that that something that pairs with everything else to give 0 has to be 0. So it doesn't have sort of a kernel, so it's non-degenerate in that way. And that gives you an isomorphism. In general, a bilinear form is a homomorphism from V to V prime. And it's non-degenerate if it's an isomorphism. Yeah.
So the Hermitian inner product isn't a bilinear form, right?
Say it again?
The Hermitian inner product isn't a bilinear form, right? It's a, like you said, sesquilayer.
It's sesquilayer, that's right, yes.
So,
Yeah, so, yeah, one has to be careful about the linearity. So this thing is, okay, so be very careful with this and go through and see in what sense these things are linear. These things are going to be R linear, and they're probably going to be C conjugate linear, or something like that. Check. And if something is so I didn't write all the C linearity and the R linearity. This statement is true over any field that has nothing to do with the reals or the complexes, because the only thing in the definition of inner product that's real or complex is the greater than or equal to 0 business. But if you take away that, then you can do this over an arbitrary field. Now, if you do this over the reals or complexes, then the manner in which this is an isomorphism from V to V prime, it's definitely R linear. I have a question as to whether or not it's C linear. It might be C conjugate linear. You should check that, please, and then let me know.
Is this proof sufficient because of the fact that we can always choose an orthonormal basis?
Yes.
Okay.
Yeah, that's the point. Yeah, so the inner product, so you should think of, okay, here's a question. What is a choice of an inner product? I'm done with lecture. Now we're just sort of discussing. We'll do Jordan form next time. So everyone should review characteristic, polynomial, geometric multiplicity, algebraic multiplicity, all that kind of thing. So next time we will start with the statement of the Jordan form theorem, and then we will explain what's going on in the Jordan form theorem and indicate how you should understand the proof in Math 501. We're not going to prove it here because the correct place to prove it is really Math 501. But we'll at least say what it means so that when you get to the proof in Math 501, you'll understand it. Now you were asking about, repeat your question?
I was just saying that the reason we can say that proof is sufficient is because we can choose one.
Right. Yeah, so here's the question. What does it mean to choose an orthonormal basis? What does it mean to choose an inner product? What is the choice of an inner product? What's the set of all possible choices of inner products? It's a great question, actually, right? So you've chosen inner products. Once you have an inner product, you do have an orthonormal basis. That's true. What's the proof? I'm looking for two names with a hyphen between them.
Graham-Schmidt.
Yes, Graham-Schmidt. Graham-Schmidt is the proof that if you have an inner product, you have an orthonormal basis. An algorithm, I can produce one. What is the set of all orthonormal bases for a given inner product?
The set of all matrices with the right, that fits back with here.
Well, it's in bijection with the set of all orthogonal matrices.
Yeah.
Right? So that turns out to be a nice group. It's a Lie group, and we will be studying that sometime coming pretty soon. I don't remember exactly the order of the lectures anymore because I rearranged them. So the point is, once you've chosen an inner product, you get all these orthonormal bases, but the set of orthonormal bases is kind of a nice set. So then the question, what's the set of all inner products? How do you choose an inner product? So you know that if you have an inner product, you have an orthonormal basis, right? Well, what's stopping me from just declaring that any basis that you happen to give me is orthonormal? I mean, if I give you a basis and declare this basis is orthonormal, that defines the inner product. Everything is a linear combination of that basis. And by linearity, I know how to take the inner product of any pair of elements. Because if you've given me a basis, right, then I just take sum of Ci, Ei paired with sum of Ci prime Ei like this. Right? What is this? This is just so now you can just expand out both sides and then use the orthonormality of the basis. Remember, you're declaring the basis to be orthonormal. Right, so you know that when you take the EI, you take the E1 term, you're going to kill all the constants except for the constant that comes on E1 over here. So this is going to be what? This is going to give you C1 prime plus Cn prime. And so what is it? It's the dot product, right? An inner product, once you choose an orthonormal basis, an inner product is always just the dot product in that basis. So to choose an inner product, just choose a basis. But if you choose two bases that are off by an orthogonal matrix, then you get the same inner product. So what you're looking at is all choices of some sort. And that some sort amounts to a choice. It's going to be the same as the flag variety that we're going to define, or the flag manifold that we're going to define. You're going to take all bases, but then you're going to mod out by the equivalence relation that says the two bases are equivalent if they're off by an orthogonal matrix. Right? So linear algebra, but it comes down to manifolds, Lie groups, and these.